Hey pre-calc, this is part 2 of section 1.4, lesson 5. It's all about the word problems again. We're going to start with number 71 on this video. So let's get to it. Every cross-section of a drainage ditch is an isosceles trapezoid with a small base of 3 feet and a height of 1 foot. So, where are my markers here? 3 feet is this measurement here. 1 foot would be the height of the trapezoid. If it's an isosceles trapezoid, that just means that this leg and this leg are congruent. If you go back to your Math 2 days, talking all about the geometry, we're trying to figure out what this unknown width of the larger base should be. This is sort of like our unknown B value. But we know that the ditch has a cross-sectional area of 5 square feet. So, by the way, guys, when you see the term cross-section, they're basically just slicing sort of like a plane straight down the middle somewhere of that. It's sort of like we've got a three-dimensional figure for this ditch, but you slice a 2D figure, you get a trapezoid. So hopefully that doesn't burden us with confusion, because we should be able to actually work through this, because area formulas for trapezoids, yes, we know what to do with that. The area formula for a trapezoid is 1/2 times the height times the sum of the first and second bases. So I think, we just call them B1, B2, smaller base, larger base, whatever you want to designate B1 versus B2. So we know that 5 square feet is the A value. The height was 1. And, well, we should make sure they're all in the same unit. Feet squared. Okay, good. A lot of times word problems will be very slippery that way. Maybe put 1 in feet, 1 in inches. Hopefully not in meters. We'll just say that this bottom base is base 1. And then the top base is the thing we're trying to figure out. So we've got this equation now. 5 equals 1/2 times 1 times 3 plus b plus 2. Use your order of operations and just, good old-fashioned math know-how. This is multiplication here. So you got multiplication, addition inside the parentheses, but we can't actually take 3 and add it to B2. So we use the distributive property to get rid of these parentheses. You can do 1/2 times 1 first, and then take that new product and distribute it to both the 3 and the B2. So 5 is equal to 3/2 plus 1/2 B2. This is the same as 1/2, so I'm just going to subtract 1/2 from both sides. Because I know 5 minus 1 is 4. Take away another 1/2, you get 3.5. Okay? And to solve that equation, you can just divide by 1/2 or multiply by 2. I'm going to multiply by 2. So this side by 2 over 1 gets rid of the 1/2. And then what you do to one side, you have to do to the other. So double 3.5 is 7. And yeah, that ends up being the length of our second base. 7 feet. Can you guys see that? Yes, you can. All right, so 71, finished. Let's try 73. All right, we're at the end of the page. Aha. All right, so 73 is talking about temperatures and clouds and all sorts of stuff that you normally don't see in a textbook for math. So it says below the cloud base, the air temperature in T at height h can be approximated by this equation. And T sub 0 is the temperature at ground level. They're asking you to determine a few things. So I'm going to use this room over here. Determine the air temperature, which is capital T, not with a little zero, at a height of 1 mile if the ground temperature is 70 degrees Fahrenheit. So the first thing I'm going to do is rewrite this equation. T equals T sub 0, also known as initial T. If you do any physics work, you might hear that. Minus 5.5 over 1,000 times H. Now, do I have to put it in parentheses? Not really. It's just, the parentheses has this calculation inside that's just acting as a, I don't know, it's just acting as a fraction. So the ground temperature is 70 degrees. So what was the ground temperature? The ground temperature was T sub 0. So we know what we can plug in right away here. 70 degrees Fahrenheit. Now it says it's got a height of 1 mile. Which, stands to reason you could just plug in a 1 right there. But H is in terms of feet as defined by this story problem. So you guys got to convert 1 mile to 5,280 feet. That used to be common knowledge. I'm not sure. It seems like nowadays less and less people actually know that there are that many feet in a mile. So the H, 1 mile, which equals 5,280 feet, because that's what H is defined in. At this point, it's just a game of plugging some numbers in on your calculator. So I did the work for you already on that, and it ends up being 40.96 degrees Fahrenheit. So it's saying that the air temperature in this case is going to be 40.96 degrees Fahrenheit. Part B. At what altitude is the temperature freezing? So altitude is basically just talking about height. So you're going to be solving for H using this same equation. It's just we're going to be plugging in some other information if we know that the temperature is freezing. All right. So what we do in this case is we say the temperature is defined right here. So we're still talking about a ground temperature of 70 degrees Fahrenheit. It's sort of like the same situations going on, but we're saying that this temperature has changed. The T that's 40.96 degrees, let's say that it was dropping, and now we're down to 32 degrees. At what height are we? So this is still 70. Height and altitude are kind of interchangeable in this scenario. So how would we solve an equation with a big fraction right there, and this is going on? Well, you're gonna get rid of this constant here first by subtraction because it's a positive 70, right? And the difference between 32 and 70 is 38. You'd keep it negative because the bigger number is being subtracted or is a negative value. That leaves you with negative 5.5 over 1,000, which, by the way, you can make this a decimal and move the decimal place 3 times to the left. I'm just going to leave it as a fraction as is. So, if we wanted to get H by itself, you could divide both sides by the number being multiplied by H, or multiply by its reciprocal. So I'm multiplying both sides by 1,000 over negative 5.5. And I already did the math on that. It ends up being 6,909.1 feet. So basically that's your altitude if all these conditions are coming into play. Let's see if we can sneak in 75 as well. All right. Wow. Swakowski's all about clouds in this section. It states that a cloud, the temperature T within a cloud, so you're inside of a cloud now, at height h above the cloud base, can be approximating using this formula instead. And they're asking us to determine the temperature at 10,000 feet in a cloud with a base temperature of 55 degrees and a base height of 4,000. And, other stuff here. So on 75, I think a good starting point would be just to rewrite the equation and try to talk our way through this. So the temperature within a cloud. So that's what we're searching for. It's at 10,000 feet in a cloud. So that H is going to be 10,000 feet. The B represents the temperature of the cloud at its base. Base temperature, 55 degrees. And a base height, oh boy. I have two height values. Let's rethink this. H represents, it's the height above the cloud base. The height above the cloud base. So let's just do a little drawing. Let's just say, here's a cloud base. Here's the... Is this where the cloud is? I'm sorry. I know what to do next. I'm struggling to kind of visualize the situation of the moment. Determine the temperature at 10,000 feet in a cloud. All right. I got my bearings. In the cloud, it's 10,000 feet. The cloud base has a height of 4,000 feet. This H value is how high it is above the cloud base. Here's the cloud base. Here it is. It's 10,000 minus 4,000 feet above the cloud base. Yeah. Sorry, guys. I think I really butchered that one. It could have gone a lot more smoothly. I'm not going to restart the video, though. So you got 55 minus... Well, the 6,000 and the 1,000 should cross-cancel just to give you 6. So 6 times 3 is 18. So it should be 55 minus 18, which gives you 37 degrees Fahrenheit. I want to check this out. All right, great. We got it.